So picture this. You're sitting there, right in the middle of a high-stakes AI and machine learning coding interview.
Oh, yeah, the pressure's on.
Exactly. The interviewer just slides a laptop over to you, and you are staring at this massive, just nonstop stream of time series data.
Millions of continuous weather sensor readings pouring in by the second.
Mhm.
Or, maybe a relentless, super noisy feed of high-frequency stock prices.
Right, and the prompt they give you, it actually sounds deceptively simple on the surface.
They always do. They basically want you to find the exact continuous window within that massive stream that has the highest overall intensity.
Which, I mean, if we strip away the real-world context for a second, you're essentially just looking for the maximum sum of a contiguous block of numbers within an array.
Yeah, exactly. That's the core mathematical problem.
So to make this concrete, let's scale that massive data stream down to a bite-sized anchor problem. You're given a specific array of numbers. Let's say it's 2, -1, 3, -2, 4.
Okay, 2, -1, 3, -2, 4.
Got it. Your mission is to find the contiguous subarray that gives you the largest total sum. So right now, I literally want you to pause and think about how you will solve this interview coding question. Because sure, the brute force method, writing a nested double loop to try every single combination in O of n squared time technically works on a whiteboard. But when you're dealing with millions of data points, an O of n squared algorithm will completely freeze the system. It's not going to get you the job. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
And today we are synthesizing a massive stack of algorithmic research papers, classic system design textbooks, and insider interview notes from top-tier tech companies.
We're doing a real deep dive into one specific super high-yield concept today.
Right, because the mission of this deep dive is to help you cross a very specific bridge. We are transitioning from being just a coder who can brute force a working script to becoming a true algorithm engineer who really understands the underlying mechanics of scalable systems.
And the vehicle we are going to use to cross that bridge is Kadane's algorithm.
Yeah, Kadane's algorithm. It's a classic for a reason.
So we need to take that sluggish, system-crashing O of n squared approach and somehow turn it into a lightning-fast O of n solution.
Which means to hit that O of n time complexity, you only get to walk through the array one single time.
One pass. You can't look back, and you definitely can't run any secondary nested loops.
Right.
So how do we actually achieve that without, losing track of the sums?
Well, it requires a complete shift in how you process information. It all comes down to a single localized decision that you make at each index as you walk forward.
Okay, let's unpack this. What kind of decision?
You have to develop a very specific mental model. At every single number you encounter in the stream, you must ask yourself one fundamental question.
Which is?
Do I continue my current subarray, or do I start a completely new one right here?
Okay, I like that. Think of your running sum kind of like your credit score.
Oh, that's a good analogy.
Right. Positive numbers are your on-time payments, and negative numbers are debts. If your accumulated debt drags your score so far down that it's literally below zero,
Yep.
you don't keep trying to pay it off using your future income. You basically declare algorithmic bankruptcy.
I love that. Algorithmic bankruptcy.
You wipe the slate clean and start a brand new financial history starting exactly at your next step. Because, I know you might have spent the last 100 beta points building up that subarray, but the sunk cost fallacy is going to completely ruin your O of n runtime.
Exactly. That mechanism right there, that is the core engine of Kadane's algorithm. If your previous accumulated sum is negative, it is no longer an asset. It is baggage.
Just dead weight.
Yep. You drop it and start fresh from exactly where you were standing. This simple logic replaces the need for all those complex nested loops. You are constantly evaluating whether your past is helping you or hurting you.
But wait, if I drop a prefix just because it's negative, what if there's a massive positive number right around the corner?
What do you mean?
Let's say my running sum drops to, I don't know, -5. And the very next number in the array is a positive 100. Am I missing out on that 100 because I reset my count?
Oh, no, not at all. You aren't missing out on the future number. You will still hit that massive positive 100 on your very next step.
Oh, I see.
You're just choosing not to attach a -5 anchor to it before you pick it up. If you kept the baggage, your new sum would be 95.
Right, because 100 minus 5.
Exactly. By dropping the baggage and starting fresh at the 100, your sum is a clean, perfect 100. You maximize your future gains by severing ties with a net negative past.
Okay, conceptually that makes perfect sense, but looking at the array, tracking all these decisions in my head sounds like a nightmare. Do I need to build a secondary array to store all my past sums?
Why would you do that?
Well, if I have to duplicate a million-point data set just to track my running totals, that completely ruins our memory footprint. We'd instantly fail the space complexity check in the interview.
You'd think so, but no, we don't need an entire secondary array at all. We just need a single mechanism to evaluate our state. We literally translate that start fresh or continue question into a single line of core logic.
Just one line.
Just one line. In your code, you use a max function. The syntax looks exactly like this. Current max equals the max of nums I, comma, current max plus nums I.
Okay, let's break that down for everyone. So
Okay.
nums I is the number you're currently standing on in the array.
Right.
And current max plus nums I is your current number plus the accumulated baggage or, well, treasure from your past.
Yes, exactly.
So by wrapping those two specific options in a max function, the computer just automatically makes that bankruptcy decision for you.
It does all the heavy lifting.
If the past brings your current number down, the max function naturally chooses to just start fresh with the standalone current number.
Perfect. So let's actually apply that to our anchor array just to see it in action. So it's 2, -1, 3, -2, 4.
Yep, that's the one.
We start at the very first element, which is 2. So our current max is simply 2. Then we take one step forward to the -1.
Okay.
The algorithm asks, is it better to start fresh at -1 or add -1 to our previous 2?
Well, adding them gives us a positive one.
Right. And since 1 is greater than -1, we keep the past. Even though the value dipped a little bit, the overall sum is still a net positive. It's still helping us.
Got it. Then we take another step to the 3. Is it better to start a new subarray at 3 or add it to our running total of 1?
Adding them gives us 4. So the max function updates our current max to 4.
Then we step to the -2. Our total of 4 minus 2 is 2. Still positive, still technically an asset, so we hold on to it. And finally, we step to the 4. Our running total of 2 plus 4 gives us 6.
Which is the correct answer. And notice what happens in the background during that single pass. We also maintain a second variable, max global.
Oh, right, because current max can fluctuate.
Exactly. Every single time we calculate a new current max, we compare it against max global to lock in the absolute highest score we've seen so far. That way, even if our current max drops later on or, plummets completely into the negatives, our absolute highest peak is safely stored in memory.
That's super elegant. But, in an interview setting, just writing the code is the bare minimum. You must explicitly declare your BigO complexity to prove you actually understand the system impact of what you just wrote.
Oh, absolutely. The interviewer is waiting for you to say it.
Right. So you look at the interviewer and tell them the time complexity is O of n because we visit each element exactly once. And the space complexity is O of 1 because we are only allocating memory for 2 variables, our current max and our max global. No matter how massive the data stream gets, whether it's 10 items or 10 billion items, our memory footprint stays perfectly flat.
And the interviewer will likely nod, but then they're going to probe deeper. They want to see if you understand the hidden architecture of the code, or if you just, memorized a neat trick from some online tutorial.
Right, they want to test your theoretical foundations.
Exactly. Because Kadane's algorithm is actually a highly optimized fusion of 2 advanced computer science concepts. It's using both greedy algorithms and dynamic programming.
Okay, hold on. When candidates hear the words dynamic programming, they usually just panic.
Yeah, DP is notoriously scary.
Because DP usually means building a massive 2D matrix to track overlapping subproblems, which takes up a ton of memory. How is this simple little 2-variable script considered dynamic programming?
Well, think about how a brute force approach actually works under the hood. It calculates the sum of elements 0 to 5, and then it separately calculates the sum of elements 1 to 5, essentially doing the exact same addition twice.
Right, which is just wasted compute.
Exactly. Dynamic programming is fundamentally just a memory trick. It's the system saying, hey, I already did this exact math a microsecond ago, why do it again?
Oh, I see.
Kadane's uses the optimized result of the previous subproblem, which is your previous current max, to solve the current one. You don't recompute the entire prefix, you just carry the optimal state forward. It is literally DP optimized down to a single state variable instead of a massive table.
That is fascinating. And the greedy aspect comes in because at every single step, we are making the absolute best local decision right now. We ask, do I keep the past or drop it? Without worrying about what numbers might be coming up 10 steps down the line. We just take the immediate optimal path.
Yep, you nailed it. Which brings us to the exact moment where the interviewer actively tries to break your code.
Oh, here we go, the edge cases.
They will delete your nice little test array and type in a new one composed entirely of negative numbers. For example, let's say the array is -5, -2, -10.
Wait, looking at -5, -2, -10. If I'm building this algorithm from scratch, I'm probably setting my current max and my max global tracking variables to 0 at the very top of the script.
Most people do.
Because that's just standard programming practice for counters and sums, right?
Mm.
But wait, if every single number in the array is negative, 0 is technically mathematically larger than all of them. Does my code just spit out 0?
It absolutely does. And you would fail the test case on the spot.
Ouch.
This is literally the #1 trap in algorithmic interviews. By initializing your variables to 0 to quote-unquote be safe, you have essentially invented a fake subarray that doesn't actually exist in the data just to protect yourself from the negative numbers.
Wow, yeah.
0 is not an option in the array -5, -2, -10. The output must be derived from the data provided.
Because if the variables start at 0, the max function sees -5 and says, well, 0 is bigger than -5, so I'll just keep 0. It literally ignores the entire array.
Exactly. It bypasses the real data. To fix this, you must always initialize both your current max and your max global with the very first element of the array. In this specific case, nums 0, which is -5.
Okay, that shifts the entire baseline. So if we initialize with -5, and then we step to -2, the max function asks, is it better to start fresh at -2 or add -2 to our previous -5?
Which would give us -7.
Right, so it chooses the fresh -2 because -2 is better than -7.
Correct.
Then it steps to -10, fresh -10, or add it to our current -2. Adding them gives -12, so it naturally chooses to just keep the -2 as our global maximum. The correct answer for the maximum subarray is -2.
And just like that, you gracefully handle the all negative array because you grounded your initial state in reality, not an artificial 0. Never ever initialize Kadanes with 0.
Such a crucial tip. So we've solved the interview puzzle, we've navigated the traps, and we proved it's mathematically sound in O of n time. But, an algorithm engineer doesn't just pass interviews, they actually build systems.
Right, the real-world application.
Yeah, so if we take this exact logic-dropping negative baggage and apply it to those massive data streams we talked about at the very beginning of the deep dive, how does this actually map to real-world machine learning architecture?
Well, in a production environment, Kadane's algorithm is heavily utilized for time series peak detection or signal optimization.
Okay, what does that look like in practice?
Imagine you have an entire year of continuous temperature data from thousands of sensors, and you need to isolate the exact multi-day period of maximum heat intensity to train an anomaly detection model.
That's a ton of data.
It is. You cannot load 1 billion data points into RAM all at once. It'll crash. You need a streaming algorithm. Kadane's processes that massive stream sequentially. It finds the peak in one single pass, and it keeps the memory footprint at a constant O of 1. It evaluates continuous data on the fly.
That connects directly back to the broader discipline of systems thinking. It honestly reminds me of how we treat database queries.
Oh, for sure.
Just as you would use SQL to efficiently filter out unnecessary rows and columns before you ever send data across the network to your processing pipeline, data structures and algorithms patterns optimize computation at the CPU level to reduce unnecessary work.
That's a great way to look at it.
Right. If your SQL query pulls millions of rows perfectly, but your Python script uses an O of n squared algorithm to process them, you just bottlenecked your system anyway. They are literally two sides of the same efficiency coin. SQL protects your network and disk. DSA protects your processor and RAM.
That is the exact architectural mindset interviewers are looking for. They want to hear that. And the overarching pattern we just covered, the running sum decision pattern, it generalizes perfectly to a whole host of other engineering problems.
Like what?
Well, once you understand the core mechanism of evaluating local state and deciding whether to keep what helps or discard what hurts, you can instantly adapt this logic. You can easily tweak it to find the minimum subarray instead. You can adapt it for circular arrays, or you can utilize it for those classic best streak and stock profit optimization problems.
It's essentially unlocking a master key for an entire category of technical questions.
It really is.
Now, to make sure you absolutely nail this, when you are sitting in that interview chair, we have a mandatory script for you. When the interviewer asks you to explain your approach to the maximum subarray problem, you need to speak aloud and communicate your logic flawlessly.
Please memorize this specific phrasing and practice saying it out loud. Just say, brute force is O of n squared. We are recomputing sums. At each step, we decide whether to start fresh or continue. We discard negative prefixes. This gives O of n time and O of 1 space.
It's short, it's punchy, and it proves you understand the architectural mechanics, not just the syntax of a random Python script. But simply listening to this deep dive isn't enough to actually build the neural pathways in your brain. You have to get your hands dirty and write the code.
Definitely. You need the muscle memory.
So we have some next steps for you to tackle immediately after this.
First is your guided practice. I want you to go write the code for the minimum subarray sum. Take the exact logic we just learned and invert it.
Oh, that's good.
Yeah, instead of dropping negative baggage, figure out how to track the deepest valley. Then, your actual homework. I want you to research and solve the maximum product subarray, the circular subarray, and the classic best time to buy and sell stock problem.
Those are all interview staples.
Exactly. And they all utilize variations of this exact same state tracking mental model.
You have your mission, algorithm engineers. But before we go, I want to leave you with one final thought to ponder. We just saw how Kadane's algorithm achieves its blazing fast efficiency by instantly forgetting its negative baggage from the past in order to maximize its future gains.
Right.
If we scale that concept up, what other algorithms, or perhaps even complex real-time machine learning neural networks dealing with continuous data streams, could become radically faster and more efficient if they were fundamentally designed to intentionally forget data at exactly the right moment?
I keep
Unpacking that, and we'll see you in the next deep dive.